It's late. You're probably staring at a terminal right now, bathed in the glow of your monitor, maybe sipping some lukewarm coffee.
Yeah, or maybe tracking down a race condition that has just been driving you absolutely crazy all day.
Oh, man. We've
Well,
all been there. Or, maybe you're just taking a minute to catch up on the tectonic shifts happening in our industry. Whichever it is, welcome. We are really thrilled you're tuning in tonight.
absolutely.
Because today's deep dive is tailored specifically for you. You are a software engineer trying to map your existing, highly logical mental models onto the slightly wild, probabilistic world of artificial intelligence.
It is a totally different paradigm.
It really is. And we have a massive stack of research in front of us tonight from the LLM Mastery Series. We are focusing entirely on this concept called word embeddings.
Right.
So our mission tonight is to basically unpack the exact mechanism of how we finally taught computers to stop seeing words as arbitrary numerical strings and start actually computing meaning.
Which was the biggest hurdle for decades.
Exactly. Because as engineers, we know the core barrier, right? If you type the word dog into your IDE, your machine does not see a furry four-legged animal that barks.
No, it just sees the ASCII encoding.
Right. It sees the number 100, then 111, then 103.
Mm-hmm.
To the CPU, dog is literally just a sequence of integers that it could just as easily represent a hex color code or a memory address.
And that absolute blindness is the historical bottleneck of natural language processing. Those ASCII values are essentially just inventory labels.
Inventory labels. Right.
Think about a barcode on a banana at the grocery store.
Okay.
That barcode tells the store's database absolutely nothing about the banana itself.
It's just an ID.
Exactly.
Yeah.
It doesn't encode the fact that the banana is yellow or what it tastes like or, its botanical relationship to a plantain.
Mm-hmm.
It is strictly a unique identifier for a database lookup.
Yep.
So for decades, if we wanted to build systems that could translate languages or generate coherent text, we were just stuck. We needed a way to turn words into numbers, because ultimately GPUs only do math, but we needed numbers that intrinsically carried the semantic weight of the words they represented.
So before we had these elegant, high-dimensional semantic maps that modern LLMs use, how were engineers actually forcing text into machine learning models? Because I imagine the early workarounds were pretty brute force.
Oh, extremely brute force. The classic engineering workaround is something called one-hot encoding.
Right, right.
If you've ever played around with basic classification algorithms, you have probably written the code for this yourself.
Yeah, it's basically a giant array, right?
Yep. You take your application's entire vocabulary, let's say it's 50,000 words. You initialize a 50,000 dimensional sparse vector for every single word.
Wow.
So for the word cat, you put a 1 at index 3,742, and you put a 0 in the other 49,999 positions.
Just imagine submitting a pull request where you instantiate a 50,000 element array for every single word in a document, and 49,999 of those elements are zeros.
Yeah, your lead engineer would have a heart attack looking at the memory allocation.
You are just begging for an out-of-memory error the second you try to actually multiply those matrices.
The computational waste is just staggering. The source material uses this great analogy. You are essentially giving every single person on Earth their own individual planet-sized filing cabinet just so they can store one single sheet of paper inside it.
That's insane. And multiplying sparse matrices full of zeros is just burning CPU cycles to calculate literally nothing.
Yeah, exactly. But beyond the nightmare it causes for your RAM, there's a much deeper mathematical flaw here. In a one-hot encoded system, every vector is completely orthogonal to every other vector.
Meaning they share absolutely no spatial relationship in the math.
Correct. The dot product of the vector for cat and the vector for dog is 0.
Zero. Wow.
To the machine, cat is just as mathematically distinct from dog as it is from the word refrigerator or the word democracy.
Right, because they're just different indexes.
Yeah. It's like giving employees random ID numbers in a giant corporation. You might have employee number 3742 and employee number 2891. They might sit right next to each other. They might collaborate on the same code base, eat lunch together every day.
But looking purely at those two integer IDs tells you absolutely nothing about their relationship.
Nothing at all.
Okay, so if sparse vectors just blow up our hardware and tell the algorithm nothing about how words relate to each other, where did the breakthrough actually come from? How do you engineer a system to understand that a cat and a dog are related, but a cat and a refrigerator are not?
This is the fascinating part. To solve a hardcore 21st century computer science problem, researchers actually had to look backward. They looked at a linguistic theory from the 1950s.
Oh, really?
Yeah, there was a British linguist named J.R. Firth who proposed what we now call the distributional hypothesis. His famous maxim was, and this is great, you shall know a word by the company it keeps.
You shall know a word by the company it keeps. I really like that phrasing. It strips away all the complex grammar rules and just looks at the raw data of how humans actually speak.
It's incredibly elegant. Firth realized that words appearing in similar contexts tend to have similar meanings. If you write a simple script to scrape a massive text corpus and just log the neighboring words, a pattern emerges.
What kind of pattern?
But while the word dog is consistently surrounded by words like walk, fetch, leash, bark, and fed. Now, if you run that exact same sliding window over the word cat, it is surrounded by vet, mouse, purr, and fed.
Ah, so they share a highly specific, overlapping linguistic neighborhood.
Exactly. Now contrast that with the linguistic neighborhood of a technical word like algorithm. If you slide a context window over algorithm, you're going to capture strings like efficient, processing, optimization, O notation.
It lives in a completely different sector of the language space.
Entirely different.
And what's brilliant about this is how perfectly it maps to human cognitive development. Think about a toddler. Nobody hands a 2-year-old a Webster's dictionary and expects them to just memorize definitions.
Right. That would never work.
Toddlers learn language purely through context, trial, and error. They hear dog used repeatedly in specific situations, and their neural pathways organically build a conceptual representation of dogness.
Which brings us to the pivotal engineering challenge. If the human brain builds semantic meaning through context and pattern recognition, can we build a neural architecture to do exactly the same thing?
So we had to stop trying to explicitly program rigid definitions into the machine.
Exactly. We had to build an algorithm that could ingest raw text, observe the company a word keeps, and basically deduce the meaning entirely on its own.
But how do you translate a 1950s linguistics theory into executable code? What did that architecture actually look like when engineers finally cracked it?
The landscape completely shifted in 2013, thanks to a researcher at Google named Tomas Mikolov. He published a method called word-to-vec.
Word-to-vec, that's a huge milestone.
It really is. It is arguably the moment the distributional hypothesis became working, scalable code. And for software engineers used to today's massive models, word-to-vec is surprisingly accessible.
Because it's not a massive transformer, right?
Right. It does not use the billion-parameter multi-headed attention transformers we see now. Mikolov used tiny, incredibly shallow neural networks.
How tiny?
We're talking about networks with an input layer, one single hidden layer, and an output layer. That is it.
Wow, just one hidden layer.
Yeah. He designed 2 specific training architectures for this, CBOW and skipgram.
Okay, let's break down the mechanics of those, starting with CBOW. I know that stands for Continuous Bag of Words. What is the actual data flow there?
With CBOW, the goal is to predict a hidden target word based entirely on the context words surrounding it. Imagine feeding a sentence into the network, but you mask out the center word. The network receives the inputs the sat, on, and the mat, and its objective function is to output the highest probability for the word cat.
Got it. So CBOW is kind of like a detective arriving at a crime scene.
Exactly.
The detective didn't actually see the crime happen, the culprit is missing, but by analyzing all the surrounding evidence, the broken glass, the footprints, the trajectory of the bullet, they deduce exactly who the unseen culprit has to be.
That's a perfect way to look at it.
So what if we flip the inputs and outputs? Does the network get better if we give it the target and make it guess the context?
That is exactly what the second architecture, skipgram, does. It takes the center word, say veterinarian, and tries to predict the surrounding context words.
Okay, so skipgram is more like a social butterfly. If you tell me exactly who someone is, I can probably predict the types of people they hang out with.
Yes, precisely. Given veterinarian, the network adjusts its weights to predict that words like animal, health, clinic, and treatment are highly probable neighbors.
Makes sense.
And from a training perspective, skipogram is actually phenomenal for rare words. Because a single rare input word is used to generate multiple context predictions, the network gets significantly more backpropagation signals to tune that specific word's representation.
Wait, hold on. This is where the whole concept feels a bit like a sleight of hand to me.
How so?
You're saying the network is frantically running forward passes, calculating loss, and backpropagating errors to get better at guessing these missing words, but does the prediction itself, whether it actually guessed cat correctly, does that even matter to the final product?
No, it doesn't. And that is the brilliant engineering trick of word-to-vec. The prediction accuracy is ultimately irrelevant.
Irrelevant.
Completely. The entire prediction task is just a pretext. It's a computationally efficient excuse to force the neural network to adjust its internal parameters. As the network churns through billions of words, desperately trying to minimize its prediction error, it is constantly tweaking the weights in that single hidden layer.
Oh, wow. So the journey was the destination all along. Once the training loop finishes, we don't care about the output layer.
Not at all.
We literally throw the prediction machinery in the trash and we extract that hidden layer of weights.
Precisely. Those extracted weights, which is usually an array of 300 dense floating point numbers for each word, are the word embeddings.
So we finally solved the sparse matrix problem.
Yes. Instead of 50,000 integers, mostly full of zeros, we have a compact, dense, 300-dimensional vector full of rich fractional values.
Okay, so we extract these weights, these 300 dense floats for every word. What makes them so special? Because, playing devil's advocate here, it sounds like we just traded one set of arbitrary numbers for a slightly more compact set of arbitrary numbers.
That's what people thought at first. But when researchers extracted these vectors and started running basic algebraic operations on them, the results literally made their jaws drop.
What did they find?
They discovered that these embeddings possessed a profound linear substructure. The numbers weren't arbitrary at all. They had geometrically organized themselves to map human logic.
I want to walk through the vector math here because this is the moment that usually makes it click for developers.
Let's do it.
If you take the 300-dimensional vector for the word king, you mathematically subtract the vector for the word man, then you add the vector for the word woman. The resulting coordinates in that 300-dimensional space land almost exactly on top of the vector for the word queen. King minus man plus woman equals queen.
Just think about the massive implications of that linear relationship. Mikolov's neural network was never programmed with a dictionary. It was never given a rule set about grammatical syntax or an ontology of royalty.
Right.
It certainly was never explicitly taught the biological or sociological concepts of human gender. All it did was ingest raw text and adjust floating point numbers to minimize a loss function.
And purely through the statistical proximity of how humans use language, the network discovered those underlying relationships.
Discovered is the key word there. It mathematically deduced that the geometric distance and direction between king and queen is virtually identical to the geometric shift between man and woman. It mapped human gender as a literal, measurable trajectory in vector space.
It mapped human gender as a mathematical direction. That is staggering. And it's not just an isolated parlor trick, right? This geometric logic applies across the entire data set.
It is ubiquitous. If you calculate the vector difference between Paris and France, it yields the exact same directional trajectory as the difference between Tokyo and Japan.
So it independently discovered the geopolitical concept of capital cities.
It discovered grammar tenses, too. The geometric shift from walk to walked is parallel to the shift from swim to swam.
It's just wild. Imagine a blind alien species. They have never visited Earth. They possess no visual cortex. They have no conception of what humans look like, how our societies function, or how we experience time. But we hand them a hard drive containing billions of human sentences. Purely by crunching the statistical co-occurrences of which strings of characters sit next to other strings of characters, this blind alien deduces the concepts of global geography, human gender hierarchies, and the linear flow of time. It is entirely discovered knowledge, not programmed knowledge.
That is the raw power of transitioning from symbolic rules-based logic to dense statistical embedding spaces. But as groundbreaking as Word2Vec was in 2013, iterating through billions of local context windows one by one is computationally exhausting.
Because you're essentially traversing the data set linearly.
Exactly. And if you're a machine learning engineer trying to scale this, you start looking for optimizations.
Was there a way to cheat? Like a way to avoid sliding a tiny window across every single sentence and instead just look at the global statistics of the entire data set at once?
That exact friction led a team at Stanford, Christopher Manning and Jeffrey Pennington, to introduce a competing architecture in 2014. It was called GLOVE, which stands for Global Vectors for Word Representation.
How did GLOVE change the approach?
GLOVE does not use a neural network prediction task at all. It is a count-based model. It scans the entire training corpus once to build a massive co-occurrence matrix.
So essentially an n-by-n grid that simply counts how many times word A appears near word B across the entire data set.
Right.
But if you just have a giant matrix of raw counts, how do you extract the semantic nuance? I mean, counting how often the "av" appears next to cat doesn't seem like it would capture the deep geometric relationships we just talked about.
It wouldn't, and that's why Glove is incredibly clever. It doesn't look at the raw counts. It optimizes for the ratios of those co-occurrence probabilities.
Ratios. Okay, give me an example.
Consider the words ice and steam. The word ice will show up frequently alongside a word like solid, but very rarely next to gas. Steam, conversely, shows up frequently next to gas, but rarely next to solid.
Okay.
By calculating the ratio of those probabilities, the algorithm cancels out the noise of common words and isolates the semantic relationship. The fact that ice and steam are related to the specific physical states of water.
That's really smart.
Glove optimizes the math so that if you take the dot product of two-word vectors, essentially measuring how much they overlap in space, that number perfectly mirrors the logarithm of how often they appear together in the real world.
And the logarithm is crucial there because it handles the massive skew of language, where a few words appear millions of times and most appear rarely.
Exactly.
So Word2Vec builds its map by essentially walking the streets of a massive city. It learns the local neighborhoods by seeing which shops are next to which restaurants, step by step.
Yeah, local context.
Glove, on the other hand, pulls up a high-resolution satellite photo of the entire city and analyzes the global traffic patterns all at once. Two totally different algorithmic philosophies, but both output these incredibly rich 300-dimensional vectors.
It really is worth pausing to truly conceptualize what that 300-dimensional space represents, because it is one of the most beautiful abstractions in modern computer science.
Oh, absolutely.
Human brains cannot natively visualize 300 spatial dimensions. Our wetware maxes out at 3. But if you run dimensionality reduction algorithms like TSNE or PCA, you can project it down and look at it. And it looks like a cosmic map of human meaning.
It literally looks like a universe.
Yeah.
You have these dense galaxies of related concepts clustering together. Happy, joyful, elated, and cheerful form a tight cluster of stars.
Right.
And then run, sprint, jog, and dash form another galaxy over in a completely different sector of the map. And connecting all these galaxies are invisible mathematical filaments of linguistic rules.
You travel along the z-axis, and you are shifting concepts from singular to plural. You travel along the x-axis, and you are shifting from present tense to past tense.
It's a mathematical universe where the laws of physics are dictated by human syntax.
That's beautifully put. Distance strictly correlates to semantic similarity, and direction correlates to logical relationships. The topology of this space is an encoded map of human knowledge, self-organized from the statistical exhaust of billions of conversations.
So, bringing it back to the engineer staring at their terminal tonight, why did this fundamentally alter the trajectory of our industry? Why do we care so much about a breakthrough from 2013?
Because it completely killed symbolic NLP.
Just wiped it out.
Overnight. The era of engineers handcrafting thousands of regex rules or manually updating giant dictionaries of positive and negative words for sentiment analysis just died. Furthermore, it birthed the paradigm of pre-training.
Right, because you didn't have to start from zero anymore.
Exactly. You could download these dense, mathematically rich vectors that had already mapped the English language and feed them into your own recurrent neural networks as inputs. Your model didn't have to learn what a dog was from scratch. It inherited that geometric knowledge.
And that workflow is the direct ancestor of the transfer learning that makes massive models like GPT, Claude, and Gemini possible today.
It is the foundation.
But as incredible as static embeddings like Word2Vec and Glove were for their time, they did ship with a fatal flaw. If you were building a production app with these tools, eventually you'd hit a wall called polysemy.
Yes. Polysemy was the bottleneck. Because these algorithms assign exactly one fixed vector to every word in the vocabulary, they completely fail when a word has multiple context-dependent meanings.
Like the word bank.
Exactly. If your input string is, "I sat by the riverbank," and later you input, "I deposited money in the bank," Word2Vec assigns the exact same 300 floating point numbers to bank in both instances.
It can't differentiate them.
The representation is static. It cannot dynamically adapt to the surrounding sentence in real time.
Which means the model is mathematically forcing the concept of a muddy river into the same exact space as a Wall Street financial institution. That is a massive bottleneck for true comprehension.
And solving that specific bottleneck, figuring out how to make embeddings dynamic and context-aware on the fly, is precisely what drove the field toward sequence-to-sequence models and eventually the attention mechanisms inside the transformer architecture.
But the math of attention is a massive topic that we will definitely dedicate a future deep dive
Oh,
to.
for sure. That's a whole other universe.
We will absolutely be digging into Transformers soon. Thank you so much for hanging out late with us and geeking out over the architecture of language. We know how valuable your time is, whether you're debugging code or just expanding your stack, and we love exploring these foundational papers with you.
It's been great.
Before you close your IDE and finally call it a night, I want to leave you with a philosophical question to chew on. If the entirety of human knowledge, from the geopolitical borders of countries to the nuances of gender, biology, and time, can spontaneously organize itself as geometric directions in a purely mathematical space, what does that imply about human thought itself? Are our own biological brains firing neurons in the dark, just executing high-dimensional vector math every single time we speak a sentence?
That is something to think about.
Something to ponder while your code compiles. We will catch you on the next deep dive.